Morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're going to talk about, well, actually we just stopped at augmented matrices, but now we're going to move on to Gaussian elimination. And this is a very, very important part of linear algebra as it is an algorithm that's used in many industries, whether that's through code or through handwriting it, but it's basically some sort of algorithm that everyone uses. Okay, so let's just hop right into it. So what exactly is Gaussian elimination? So Gaussian elimination is basically what we did in the previous example, right? Where we did elementary row operations in an augmented matrix, right? That's basically what Gaussian elimination is, bottom line. Right. So then after we do Gaussian elimination, the resulting matrix is in echelon form, or what we call row echelon form. If we have elementary row operations, we have row echelon form, and they will have certain properties, right? Okay, so let's just, I'm just gonna go through the book. So here's some, I guess some buzzwords. Maybe that's why they put it there, but one is Gaussian elimination, obviously. Another buzzword that we might encounter is echelon form, which we already talked about for quite a while. And another thing is this idea of the leading term. So the funny thing is, from linear systems to augmented matrices, this is just going to be slowly building up these concepts, right? So we did Gaussian elimination, right? And so doing Gaussian elimination results in a matrix in echelon form, or in echelon form, right? Bottom line, that's what that means. Okay. And there are some properties. Okay, so I'm just gonna say it out loud, but there will be a definition after this. And in that particular definition, there's or the leading term, so that's where the leading term comes in, of a row is the leftmost non-zero term in that row. Okay? And the row of all zeros has no leading term. So let's just that definition. So this definition is telling us that if we have a matrix in echelon form, we say a matrix is an echelon form if, well, one is every leading term. So leading term is the same as leading variable in this case. So if we have every leading term is in a column to the left. So it's in a particular column in the augmented matrix to the left of the leading term below it. Now, what in the world did I just say? What I said is, say we have a matrix. Let's say it's an echelon form. Let's do an augmented one. Why not? Let's do 1, 2, 3. Put that bracket there. 0, 0, 0, 4, 5, 6. Oh, shoot. This one doesn't have a solution. I'll do 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 1 This has a solution. 0, 0, 0. So this is an echelon form in the sense that every leading term, where are the leading terms? These two. So every leading term is in a column to the left. So it's in a column to the left of the leading term below it. This is the leading term below, and the other leading term is in a column to the left, if that makes sense. Okay? I hope that makes sense. Right, so that's one property that we have to consider. Another property is that any 0 rows, oh shoot, I should have put back the example. 1, 2, I forgot. 3, 0, 4, 5, 0, 0, 0. Okay, say we have the augmented matrix. Any 0 rows are at the bottom. So this one's pretty self-explanatory, right? Like if we're given this augmented matrix, we can see this is a 0 row. Row 3 is 0, is a 0 row, and it's at the bottom. And so we know this is a matrix in echelon form, right? It satisfies the first property where every leading term is in a column to the left of the leading term below it. And it also satisfies the other property that any 0 rows are at the bottom of the said matrix, right? Okay, so I'm gonna quickly copy this into my big vocabulary of definitions. A lot of vocabulary. Might go through these in one video maybe, give an example of each, but we'll see. Couple of definitions. Right, so that's that. Okay, so let's note, oh yeah, so fun fact, echelon form is the counterpart echelon systems, right? They just build up on each other, but it's really, we're talking about the same thing, just for matrix, right? We're actually talking about the same thing, but we're just translating it into matrices. Okay, let's note that the first condition in the definition, right, implies that a matrix in echelon form will have zeros, filling out the column below each of the leading terms. Okay, we have some examples. I'm not going to show them anymore because we already looked at them. Let's talk about a few more buzzwords or a few more definitions. We're going to talk about what exactly are pivot. Pivot positions. I think the next one are columns, right? Pivot columns. And then just pivot. So what exactly are pivot positions? Basically, pivot positions, they are those that contain leading term in the matrix. So this is not necessarily the number, but it's the position or the place. So we think of it like, so we have this example again. 2, 4, 5, 6, 7, 8, 9. Say we have that matrix, right? This is an echelon form, right? It satisfies that first, man, I can't even say that first. That every lead, I can't say this one, but basically it satisfies that, right? So every leading term in a column is to the left of the leading term below it. Okay, we got it. Doesn't satisfy the second one because there are no zero rows, but it satisfies the first one, so most likely it is an echelon form, right? Okay, what are the pivot positions here? This is a pivot position. This one. I'm talking about the place at which they are at, not necessarily the numbers. It's just the position or the place. Okay, those are pivot positions. Pivot columns, lots of definitions. So basically the columns that contain pivot positions. So here we can see we're actually building off of what we said earlier. Do that matrix again. This is an echelon form. These are the pivot positions. And apparently we can see that all columns 1 to 3, all of these columns have a pivot. So therefore all the three columns are pivot columns. We can say they're pivot columns, right? Because they contain a pivot position. And lastly, let's now talk about the actual pivot. What is that? So the actual pivot is basically now the number. So to be more specific, it's a non-zero number. And where is it located? In the pivot position. So just like the matrix earlier, keep writing it out. Maybe I should have just... These are pivots, 1, 7, 9. Pivot positions are the places at where they're at. Pivot columns are these. Because all of them contain a pivot position. Okay? We can connect all of these together, but that's basically what it is. Cool. Okay. Okay, we have a very general idea of what an augmented matrix is. I'm not gonna write that out anymore. It's not that important. Let's do an example. Let's keep practicing this idea. So let's do example 4. So here we want to find all solutions. Actually, we've been doing this a couple of times now to linear system. Right, so we have 2x sub 1 minus 2x sub 2 minus 6x sub 3 plus x sub 4, and this is equal to 3. Then we have minus x sub 1 plus x sub 2 plus 3x sub 3 minus x sub 4. This is equal to negative 3. Then we have x sub 1 minus 2x sub 2 minus x sub 3 plus x sub 4. And this is equal to 2. So what do we notice? Actually, I don't notice anything. I'm messing I'm messing with you guys. But basically we want to use what we've been doing, right? So you want to convert to an augmented matrix. So we can do that. So we have 2, negative 2, negative 6, 1. Constants are 3, negative 3, 2, negative 1, 1, 3, negative 4. Shoot, 1, my bad. Now I got confused with the coefficient and the subset. Negative 1, Then we have 1, -2, -1, 1. So we just get quicker doing this because we can easily see the coefficients in the linear system. Right, so what is this? We want to make them into echelon form. How do we do that? Well, we can make this thing a 0. Here's how I would do it. I would do row 2, add it to row 3, put all of that in row 3. So I keep row 1 as is. I keep row 2 as is. Then I add the stuff. This becomes a 0. This becomes a -1, 2, 0, -1. Okay. Now I want to make this upper thing a 0. How do I do that? I could do row 1 divided by 2, right? Or add it or multiply it by a half, row 1. That becomes a +1. Then I add it to row 2, put this in row 2. So if I divide this, this becomes 1, -1, -3. 1 becomes a half. This becomes 3 halves. Okay. Then I can copy row 3, right? And then we have row 2 here. So we just add it. 1 minus 1, 0. -1 plus 1, 0. -3 plus 3, 0. Or 1 minus 1? Or no, a half minus 1. So it's -1/2. Then 3 halves minus 3. Minus 3 is 2, 6. -3 halves. Okay. Working on the fractions here. Do we have it in echelon form? Not yet. So now I'm thinking, well, we made all of these zeros, which is funny. I could just switch row 2 and 3, and be over with it, you know? So row 2, switch it to row 3. 1, -1, -3, a half, 3 halves. So I save row 1, so it becomes row 2 now. Then I have row 3 here. And there we have it. Done, right? We now have it in echelon form, I think. If not, then that's funny. But I do think we have it, though. Okay. Wait, let me just check. Has to be. Yeah, I do have it. Yeah. Oh, got the exact numbers. I just multiplied. Oh, so what he did now was he multiplied by 2. Because it's nicer. To row 1 and row 2. Oh, no, shoot. 3. Okay. From textbook. Yeah, I could multiply all of these by 2 just to cancel out that fraction, make it nicer. So I could do that. Or actually, it's fine. Yeah, I'll stick to this. I'm okay with fractions. Not like, yeah, right. So anything else? Yeah, we just apply back substitution here. So what do we see? We see negative a half of x sub 4 being equal to -3 halves. Right? And well, from here we can just say x sub 4 is 3. Make sense? And then the second row is negative x sub 2 plus 2 x sub 3 equals -1. Okay? Now here we see that x sub 3 is a free variable. right? Actually, shoot, that's the first thing we should have done. I almost forgot. We have to identify the leading variables and free variables. So where are the lead variables? So leading variables are, or lead variables. We say x sub 1 is, x sub 2 is, x sub 4, right? While x sub 3 is free. So we call this a free variable. And so we set a free parameter, s sub 1, where s sub 1 is a free parameter. Okay, just to make the proof a little bit more concise, we say that this s sub 1 free parameter belongs in the real number set. So meaning it's a number, right? Can't be something else. Oh shoot, the p is left behind. Nice. Okay. So to complete this thing, x sub 2 plus 2 s sub 1 equals, did I say negative 1? I did say negative 1. And we say x sub 2 is 1 plus 2 s sub 1, right? And lastly, for x sub 1, we have x sub 1 minus x sub 2 minus 3 x sub 3 plus a half of x sub 4. And to substitute everything, minus x sub 2. So the value of x sub 2 minus 3 s sub 1, value of x sub 3 plus 3 half. And we say this is half. Oh, means these things are 0. And so from there we say x sub 1 is something. 1 plus 5 s sub 1. So those are our solutions. I'm going to write it out anymore, but basically here. And since we have a free variable, we say that this system has an infinite number of solutions. And that satisfies one of the properties of an echelon system, or a matrix in echelon form, same thing, right? Also, this is an echelon form. Reason is, well, for one, leading variables are sort of like a staircase. It's to the left of leading variable of a column, to the left of the leading variable below it. I still can't get over that definition. But we don't have anything for the other property because we don't have an all zero row. Okay. So yeah, that's it. Infinite solutions. That's all we can say about it. Okay, let's try another one. Oh shoot, I don't want to try this one. There's just so many stuff. Okay, a lot of examples actually. Let's actually move on and let's do Gauss Jordan. There's another thing. Gauss Jordan elimination. Because I don't want to get too bogged down with Gaussian elimination. Okay, well, for starters, what in the world is this? So Gauss, okay, there's a German engineer who did this thing. What is this? Okay, a lot of computations. What? Okay, let me just say it. Okay, because the example is pretty weird. Hmm. Okay, I'm trying to think of a way to say this without the example, but it doesn't tell it what it is. Okay, I'm just gonna say it. Okay, I'm gonna start with an example. Sure, let's do that. So the example is we have this big, really big matrix actually. 1 0 0 0 0. How many entries is that? Oh shoot. I I increased the entry. It's only 4 rows and 6 columns. 4. Then we have 3. Goodness me, so many. We have 2 or -2. Oh, that's fine. And then we have n -3 1 0 9 -2. Oh, so many stuff. 0. And then behind that, or to the right of that vertical bar, you have these constants. So we actually have a 0 row here. I don't know, just an observation. This has nothing to do with Gauss-Jordan. Here's what Gauss-Jordan is. I'm gonna say this matrix, or after a couple of operations, this matrix is equal to this thing. We have 1 0 0 0 4 0 0 0 0 1 0 0 -2 0 0 0 0 0 1 0 4 5 -1 0 5. Oh, this is the last one. -5 -14 3 0. So again, we have that 0 row, but there is a difference, right? You guys can tell. No, but there is a difference. Difference is that here we actually see a couple of things. Now you guys can see it, but I can't, so believe me. We see these, if we look at these particular columns, what does that mean? Well, for one, they are the leading terms. That's one. We have a leading term here. So we call these pivots, right? So we have pivots here. These 3 are pivot columns. Okay? So these 3 are pivot columns, and these 3 are pivots. And where they're at are pivot positions. But besides that, we can see that the leading terms are all 1. The pivots are all 1. And that's the only entry in this pivot column that's non-zero. So let's actually write down what we observe. So we actually observe, let's just write it down. So here are our observations. One, we see, okay, this is not from the book. This is just me doing it. One, we observe that all pivots are 1. That's one thing we observe. 2, all pivot columns have only 1 entry, which is 1. That's it. That's what we've observed. Oh yeah, another thing. Matrix is in echelon form. Let's not forget that. How do we know? Well, it follows the properties, right? We can see this leading term is a column to the left of like two columns after, but two columns after, or yeah, the leading term below it is, well, it's to the right. And then we keep going to the right, same idea. Okay. So in the definition, it tells us to the left, but it doesn't tell us exactly how many columns to the left. It just tells us to the left. So we can safely say that this matrix here is an echelon form. And considering that we've seen these observations, so actually, let me just write it out. Here's the actual definition for it. So actually, these three observations mean something. They have a meaning to it, right? So here's the meaning. You have a definition here, 1.5. I don't know why they put these numbers, but basically, a matrix is in. So here's the thing. It's in reduced echelon form. We have an echelon form and we have a reduced echelon form. Or another way we call it, row reduced. Or shoot, did I mix it up? Oh shoot, I mixed it up. It's reduced row. Reduced row echelon form. If here are the properties, and I think we've seen this, right? Well, for one, it is an echelon form. So that checks this out. It's in, that checks out the third observation that we have. The all pivot positions contain a 1. So this property here is very similar to this thing. All pivot columns have only one entry, which is 1. Okay. And then last property, the only non-zero term in a pivot column is located in the pivot position. And that checks out our observation 1. Right? So this is similar to saying all pivots are 1. Right? Oh no, actually it's also 2. Oh yeah. Yeah. So these 3 mean reduced echelon form. That's actually the definition. We just formalized that here. Okay. So that's the thing. So the fun thing about, or no, not really the fun thing. The thing about, or at least the course I'm taking right now, is it focuses so much on reasoning and really getting all of these definitions down. So I'm just trying to do that. Then by the end of me reviewing for the midterm, I'm going to have a whole lot of definitions and theorems at the back of my head. Right? Or most likely I'm going to put these in a cheat sheet. Maybe they'll ask us to write a proof about something. Then I can refer to these definitions. Great. So you have some particular examples here. You know what? Let's put one of them as an example. Let's do this. How many rows? Four. Okay, we keep going. Oops. Yeah, it's more like a logical reasoning class. It's not really like a math class. It's more like how do you explain that these are valid, you know? Oh shoot. So this here is a matrix, not an augmented one. So that means we don't have any constants to the right. This by itself are the coefficients of of the matrix. Okay, so is this in reduced echelon form? Well, for one, it is in echelon form. Why? The pivots are where are the pivots? Pivots are here, here, here. And they are well, they're in okay, I'm just gonna say they're in descending order. That sounds better than saying the leading term to the column at the left is blah 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 blah. So let's just do that. Okay, so it's in descending order, right? And we have a zero row and it's at the bottom. Okay. So let's just say descending order. So here we're just writing down our observations. It's in descending order, zero row at bottom. So that means it's in echelon form. So that checks out one of them. But how do we know if it's reduced? Well, we need to check the pivot columns. So these are the pivot columns. What exactly is a pivot again? A pivot has a leading variable or a leading term, I mean, not variable, leading term that has a non-zero. So that doesn't include the first column because the first column are all zeros. So that's not a pivot column. Second column, third column are pivot columns. Third column, no, not third column's not. Okay. Fourth column is a pivot column because it does contain a pivot here, right? Great. What else do we have to check? We have to check if the only entry in that pivot column is in the pivot position. And in that pivot position, the entry is 1. So let's break it down. The pivot position, does it have 1? Yes. Is it the only entry in that column? Yes. So we know it's in reduced echelon form. Right? That's how we know. I'm not gonna write all of that out. Basically, that's how we know. So this thing is RREF, reduced row echelon form. Let's try to do something a bit cooler than just it's actually more terminology here. Let's do forward. So more buzzwords here. Forward phase, backward phase. Then we have Gauss-Jordan. Oh yeah, shoot, I forgot to mention, what's Gauss-Jordan? If Gaussian elimination is to make a matrix in echelon form, Gauss-Jordan elimination is the same thing, but to make it reduced echelon form. They're literally the same thing, but you do the same thing until you get a reduced echelon form. And that's Gauss-Jordan. That's it. Is Gauss-Jordan that means elimination. Right. So I hope that makes sense so far. Hopefully I'm not going overboard or okay. Let's see. So transforming a matrix to reduced echelon form can be viewed as having two parts, right? So when we want to transform a matrix to reduced echelon form, so transforming matrix to RREF, reduced row echelon form, that's what it means, has two parts. Just like a movie, you have an intro and an outro. I'm kidding. You have two parts to it. So bad analogy there. Forward phase. Actually, I'll just put backward phase. Backward. Put forward. Gaussian elimination. So it's doing elementary row operations again and again until we get to echelon form. Not reduced, but echelon form. Put backward phase. Basically, it completes the reduced RREF. So that's when we continue doing Gaussian until we get the reduced row echelon form. And basically, what we're saying here is both forward and backward phase is Gauss-Jordan. So doing both, that's Gauss-Jordan, right? Okay, an important note, I think is pretty important. I'm already in green. Now here's a quick question. How many echelon forms can we have of a linear system? Say we're given a linear system, we convert it to an augmented matrix, we do elementary row operations, we somehow end up with an echelon form of that matrix, right? How many different echelon form matrices can we have? In fact, we can actually have a lot. We can have a lot of possibilities of echelon form matrices, but for reduced echelon form matrices, that's not true, right? So here, so we can have infinite actually. You can have infinite echelon form matrices, but only one reduced row echelon form matrix. Matrix. Yeah. So that's what that means, right? Like I could tell you, say we have, looking at the example, this one's an echelon form. I could literally multiply this row by 2 and get a new matrix that's still the same. It's still an echelon form, right? Or I could, what else could I do with that? So that's one possibility. Now I don't see my notes. Great. I could, what else could I do? Actually, mm, there are a lot of possibilities. I'm just not getting one. You could, let me see. You can make this positive and then make row 1 positive and then add it to row 2 and then put that in row 2. Oh, actually, you can't do that. Yeah, this would make it 0, but this one wouldn't. So my bad. Never mind. You could scale everything. You could multiply these row 1 and row 3 by 2. But basically, there are a lot of possibilities. I'm just putting it out there. I can't really do it on my own. But infinite number of possibilities. But for reduce, well, that's only one thing. You only have one. And it's easier to back substitute with reduced echelon form matrices. Okay, here we have a theorem. We say a given matrix is equivalent to a unique matrix in reduced echelon form. If we have a matrix, we do Gauss-Jordan, we get it to a reduced echelon form matrix. It's the same thing as the original matrix. That's basically what this theorem is saying. I actually relate both theorems here. We have a lot to look at here. Right. Let's keep going. Okay, so we have an example of doing Gauss-Jordan. I am not gonna do that. That's gonna take way hella long. Okay, more Gauss. Lots of proofs as well, but yeah. Okay, let's just go through this and then take a break. Now we have another new thing that we want to talk about. So probably we're gonna go back to linear systems, right? Yeah, just to backtrack for a bit. We're gonna talk about homogeneous linear systems. What in the world what in the world did I just say? I don't know. We'll find out. I'm kidding. I know, but like we're gonna find out. Homogeneous equation. So there's some buzzwords here. Homogeneous system. So going back to the idea of literally the first section 1.1, we go back to this idea of what is a linear equation? What is a linear system? A linear equation, well, it's an equation that defines a line, right? And a linear system is a couple of linear equations put together, right? It's a set of linear equations put together. So what is a homogeneous equation? Or to be more precise, a homogeneous linear equation? Well, we say the linear equation is homogeneous. So we describe it as a homogeneous if it's in the form. So remember how for a linear equation we do a sub 1, x sub 1, a sub 2, x sub 2. We keep going to some value, says in the book n, and we say it's equal to b. Well, we change b to 0. That's it. It's an equation equal to 0. A linear equation equal to 0. That's what a homogeneous equation is. Now, what's a homogeneous system? What do you think? Well, it's made up of homogeneous linear equations, and they're all equal to 0. That's what it means. So, a homogeneous system is in this form. I'm just going to write out the form. Is in this form. So we're really just bouncing off ideas here. So this is a sub 1, 1, x sub 1, a sub 2, 1. No, not 2, 1. 1, 2. My bad. We'll learn about these indices in a bit, but should we go all the way to, say, n? N. And you go 2, 1, so 1, 2, 2, so 2, all the way to 2n, sub n. Keep going, keep going. We do m1, x sub 1, m2, x sub 2, m n, x sub n, and all of these things are equal to 0, right? So this is a homogeneous system. It's a system made up of homogeneous linear equations, and they're just all equal to 0. Oh yeah, fun fact. We say that all homogeneous systems are, so we say they are consistent. What does that mean? Because there's always a solution. If we go back, or I didn't really discuss this, but I think we discussed consistent, inconsistent. Yeah, I did all of these again. Can't find it in the first section. Did we discuss it? Or if we didn't, I'm just gonna say it. I don't think we did though. That's funny. You didn't do it. Really? Oh, there we go. Consistent, inconsistent. There. What's the condition? If a linear system has at least one solution, then it's consistent. Otherwise, it's inconsistent. Now here we say all homogeneous systems are consistent because there's always a solution. And what's the solution? Are numbers a, or no, not really a, let's do x sub 1, x sub, actually, we say that x sub 1, x sub 2 are equal all the way to n. They can just be 0 and everything's just going to be good, right? If we make this a 0, we make this a 0, everything is 0, then the sum is going to be a 0. So it always has that solution. And I'm probably gonna point it out. Trivial. In other words, easy. In other words, not super important or obvious. And we're actually gonna go through that. So here's the next buzzword. Trivial solution. And of course, what's the opposite? Non-trivial. So we have two more buzzwords. So what's a trivial solution? A trivial solution is the obvious solution. But if there are other solutions, then they are, check my handwriting, non-trivial solutions. Right? So that's that. Okay, you have more examples, more examples, more examples. Okay. Blobs. Been a while since I've looked at that. Okay, let's actually do a proof of one of the theorems here. This might not be in the test, but I'm going to do it. Figured it's nice to prove stuff. Hope so far. I'm going to take a little pause, but I hope so far everything's good. No issues with anything. And we're kind of getting all of these, hopefully. Right. Let's actually prove theorem 1.3. So again, it's theorem 1.3. I'm just gonna copy paste. I'm not gonna do that. I'm not gonna memorize like, hey, what's theorem 1.3? Let's prove this thing based on what we know. This is the proof, right? If we have a linear system, it's either going to be three things. It's going to have no solution, one solution, or infinite. How do we prove that? So here's the proof. So say we take, of course, we want to make it general. We take any linear system, we form, so what we've been doing, we form an augmented matrix. And then we use Gaussian elimination. To make the matrix to echelon form or to reduce to echelon form. So what we've been doing, right? Now we have it in echelon form, right? Let's say we do have it. And what we do is we back substitution to get solutions. So we extract the transformed system. Really wordy. And what can we say? When we extract, we can either have three outcomes. One's one's zero solution, one's one solution, one's infinite. So here are the three outcomes. So system has an equation. I think this is the no solution one. Of the form 0 equals C. For C not equal 0, in this case, no solutions. So really what the proof is telling us is why. It's really just explaining how the theorem is true. We make a statement, we explain it. It's not necessarily more mathy stuff. It's more about explanation. So we can think of this. We can think of this. We can think of this as a trick. Then we can think of this as a why. So explain, why is this true? B, the system has no free variables. So it could have no free variables, right? So we don't set free parameters. And hence only one solution. That's it. We just make do with what we have, right? Lastly, system has free variables. System has at least one free variable. So infinite solutions. Even one free variable could lead to many solutions. That's how we prove this thing. Okay. Now, homogeneous linear systems are even simpler since all such systems have that trivial solution. Let's actually apply our proof here. So say we're given a homogeneous linear system. A cannot happen because C is always going to be 0. Our constant is always going to be 0. So here's a fact. So we're just connecting dots here, but basically for a homogeneous linear system, A cannot happen, right? Since C is always 0. Hence, it's either the system, I mean. Hence, the system is either one solution or infinite. It's only one of those two, right? So if we're given a homogeneous linear system, we can think, okay, this is either going to have one solution or infinite solutions. What am I doing? And yeah, I think, yeah, that's it. Lots to cover, lots of new jargon, but I hope everyone learned. And yeah, proofs are kind of fun. I mean, you just explain why something is true. Not necessarily, you don't necessarily have to do math. It's more or less an explanation. So yeah, that's pretty much it for this video. I hope you guys enjoyed, and I'll see you all in the next one.